All right, everyone, this is part two of the water PowerPoint, part two of the water notes. We're going to pick up with adhesion. Adhesion is the opposite of the last thing we talked about, which was cohesion. Cohesion was the attraction between like substances, and adhesion is the attraction between two different substances. All right, so water will make hydrogen bonds with other surfaces such as glass, soil, plants, tissue, and cotton, things like that. The main, I guess, thing I want you to remember about adhesion is that it causes capillary action. That's capillary action. It's when the water molecules will like tow each other along when they're in like a thin glass or a straw or even up a paper towel. Okay, so it's pretty much when the water is attracted to the other substance and will pretty much kind of move itself along that other substance. Excuse me. The example is transpiration. It's a process in which plants and trees remove water from the soil. That's an example of it. So you know how when you water a plant, you don't actually water. Well, sometimes you put water on the leaves and everything, but the plant is getting the water from its roots. It's soaking up the water from the soil all the way up into the actual, stem and everything. All right, and that process is called transpiration. All right. We said earlier, adhesion causes capillary action. This is an example over here of a straw being put into a cup of water, and as the straw is put into the water, you see the water rising up the straw, kind of towing itself up the straw. Okay. So the whole thing is that capillary action gives water the ability to climb structures. Okay, same thing if you put a paper towel in a bucket or a little container of water like that and just dip it in like that straw's dipping in, you'll see the water start to tow itself up the paper towel as well. All right, adhesion causes water too. If you look on the left, you see how the water molecules are lining up. And over on the right, that's a spider web where you see the water molecules attaching to the spider web. It's kind of beating together up. So where the water's kind of hanging together on the actual other substance. And then down at the bottom, you have a leaf where water is dripping, but it kind of beads up into a little ball on the leaf. That's because of adhesion. All right, our next property is high specific heat. Water has a high specific heat. And what that means is basically it's the amount of heat needed to change 1 gram 1 degrees. So basically that means it's the amount of heat needed to change the temperature of water. Because water does not like temperature change. All right, water resists temperature change both for heating and cooling. So the best example that I give is when you go swimming and if it's the summertime and in Georgia it's hot. So if it's the summertime and it's maybe, I don't know, 9:30 in the morning. So maybe the sun has only been up for about 2.5 hours or so. When you get into the water, if you just run and jump in, the water's going to be cold. All right. If you swim all day and then, let's say you swim for a couple hours, you get out, you go home, do whatever you normally do, and then you come back at like 10 p.m. Okay, the sun is down, but the sun's only been down for about an hour or so. If you go jump in the pool, it's going to be warm. That's because the pool, remember when you got in at 9:30, it was cold, but all throughout the day it had the hot sun shining on it, and the temperature was very high. So it took that long amount of time for the temperature to rise in the water. And then just because the sun went down, at 9 o'clock, and now it's 10 o'clock and you're going swimming again, that little 1 hour is not enough time for that water to change temperatures. Remember, because water resists temperature change. So at 10 o'clock, it'll still be warm. And then once you get out, and then, the sun has been down since about 9 o'clock. So then from 9 to 10, 11, 12, 1 in the morning, 2 in the morning, 3 in the morning, 4 in the morning, 5, 6, 7, 8, 9. And then you go swimming again, it's had that whole long period of time to cool off. So that's why it'll be cold in the morning. All right, so key thing to remember is water resists temperature change. And water can absorb and release large amounts of heat with little change in temperature. Okay. All right. Next property is high heat of vaporization. High heat of vaporization. It's the amount of energy to convert 1 gram of a substance from a liquid to a gas. Okay. The big takeaway is it's the amount of energy needed to convert a liquid to a gas. All right. In order for water to evaporate, hydrogen bonds must break. And as water evaporates, it removes a lot of heat. All right. Best example for these is if you are cooking. If you ever made anything on the stove where you're boiling water, if you put water in on a stove and you turn the eye on and it starts to heat up, you can put your hand in the water as soon as you put it in there and it's not going to be hot. But if you give it a while, once that temperature gets high, it's going to start boiling and boiling, and once it sits there for a long time, it's going to boil and start to evaporate. You can see it literally going from a liquid to a gas. That's the high heat of vaporization. It means that it takes a certain amount of energy to change that liquid to a gas for evaporation to happen. And at the bottom where it says, as water evaporates, it removes a lot of heat. That's your body's, that's pretty much one of the reasons why you sweat. Okay, when you're really hot and your internal temperature starts to increase, your body starts to sweat, and it puts that cool sweat on the outside of your hot skin, and then your body will the heat of your body will evaporate that water, and when that water evaporates, it's removing a lot of heat from your skin. Your heat is dissipating from your body, and it helps cool you down. And that's just a mechanism that your body uses to help try and maintain homeostasis. All right, let's keep moving. Key takeaway from this slide is just that as water evaporates, it removes a lot of heat. Okay, and that's the cooling effect I was talking about with the sweating and how your body is trying to maintain homeostasis. So the first two bullets, they aren't really important. You can just focus on the last one. It says, as water evaporates, it removes a lot of heat with it. All right. And this is kind of, I don't want to say extra information, but that's why when you hear people talk about global warming, that water vapor, it acts like an insulation. Okay, and the water vapor, and all the different gases that are in the atmosphere, they kind of, stay around towards the perimeter of the Earth, and they're holding in a lot of the heat energy, or a lot of the energy that comes from the sun that would usually reflect and come, off the Earth and come back out into space. It's being kept in the Earth because of those different gases that are, gases and water vapor that are all around the surface of the area. And that's helping to increase the temperature of the air of the Earth, which is global warming. We'll talk more about that later when we talk about the carbon cycle. All right, water is less dense as a solid. So it means when it's frozen, when it's ice, it's less dense than when it's a liquid. That's why ice floats in a river or a lake or even in a cup of water. In liquid, water has hydrogen bonds that are constantly being broken and reformed again. And when water is frozen in ice, it forms like a crystal-like lattice structure to where the molecules are set at fixed distances. So they're not going to be moving and breaking and moving all around. They're going to be stuck in those fixed distances away from each other. That's why it's less dense. Okay. Here's just a little question. Which is ice and which is water? Look at these little images down here, and you have pretty much, this is the, I don't want to say the water molecule, but because it's a lot of water molecules in here, but basically within these lines right here, which one seems to be more compact and which one seems to be more spaced out between these two? All right, so the one that's more spaced out, that will probably be the ice, because they're at, the molecules are all at fixed positions and they're not going to be moving in and out too much. So the one that's less dense is probably going to be the ice. There you go. So this one is more compact, closer together. All the molecules are closer together in the water, meaning they're more dense. And then over here, they're less compact, meaning less dense, or you could think about it being less condensed. If something is condensed, it's real close together and packed in. All right, we talked about homeostasis in a couple of the previous units. Homeostasis is pretty much the ability to maintain a steady state when the environment is changing. Okay, so it's maintaining a steady state despite the changing conditions. So if things are changing around you, you're still maintaining the same regular conditions. And water is important for this process because it does a few things. Water is a good insulator. Insulator is something that helps you maintain temperature, whether you're going to keep warmth in or keep cool in. Either way, it's a good insulator. We said earlier, water resists temperature change. And see, this actually is another one of the properties of water. It's a very important one. It says water is the universal solvent. Water is the universal solvent. Being a universal anything, that means that, say if you have a universal remote at home, okay? It's a universal remote. That means it won't just work for the TV, but it'll work for the TV, the DVD player, a stereo if you have one, multiple things, because it's universal, right? It can work for more than one thing. So a solvent, as we know, a solvent is something that dissolves something else. So a solvent is whatever something is dissolving in, right? It's the thing that's doing the dissolving. So if it says universal solvent, that means pretty much that it can dissolve a lot of things or almost everything. So believe it or not, if you take anything and put it in a lot of water and leave it there for enough amount of time, it will start dissolving. Whether it's wood, sugar, metal, probably, honestly, because it'll start rusting. So it'll start breaking it down as well. It's a universal solvent. That means it'll pretty much break down or dissolve anything if you give it enough time. And that last one's pretty important. Ice protects against temperature extremes. That's why, if you have a frozen lake, it freezes on the top, but underneath it's not frozen because the ice is insulating it, the bottom of the lake, and so the bottom actually is warmer than the top of the lake is when the top is frozen. Because remember, ice floats. All right, we're going to move on from this one. All right, we will talk about this. We talked about this earlier when we talked about isotonic, hypertonic, and hypotonic solutions. We talked about solute and solvent. So this is just kind of like a review. The solute is the substance that is being dissolved, and the solvent is the substance in which the solute is dissolving. Okay? So the the solvent is doing the dissolving. It's actually dissolving things, and the solute is whatever is being dissolved. All right, we're going to skip this one. All right, here we go. Acid, bases, and pH. Pretty much, this one is saying that water, we know, is H2O over here on the left. Let me get the cursor up. And I don't see it, so let's move on. Water is on the left, the H2O. It can disperse or disassociate and break up into a hydrogen ion on the left, and then a hydroxide ion on the right. Okay, hydroxide, remember, that's kind of what denotes or what exemplifies or displays or what means base. Remember when we talked, actually we haven't talked about it yet. So think about the more hydroxide ions you have, that's the more basic you are, or the more of much more of a base you are. Go back. And the more hydrogen ions, or hydronium, which is the H+, that's the more acidic you are, the more of an acid you are. All right, so now we're going to talk about the pH scale, because we're talking about acids and bases, and that's pretty much what the pH scale is measuring. So the pH scale indicates the concentration of hydrogen ions. All right, so remember, we talked about concentration before. Concentration means the amount of, or a large number of, or could be a small number of. It's just talking about the amount of whatever else you're talking about. So in this case, it's the amount of hydrogen ions. All right, so the pH scale going from bottom to top, it ranges from 0 to 14. The scale ranges from 0 to 14. Right in the middle, the pH of 7, that is neutral. If you have a pH of 7, it's called neutral. All right, a pH from 0 up to 7 is an acid. That means you have, you're producing more hydrogen ions, which is the H plus. And if you are a pH above 7 and between 14, and so basically between 7 and 14, that's a base, or it's more basic, meaning you're producing more hydroxide ions, the OH negative. All right. Each pH unit represents a factor of 10 times change in the concentration. So that means if something is a pH 3, it's 10 times 10 times 10, which is 1,000. So it's 1,000 times stronger than a pH of 6. So if you have a pH of 6, you're 1,000 times weaker than a pH of 3. That means a pH of 3 is 1,000 times stronger than the pH of 6. Okay? So each time it increases or decreases by a factor of 10. All right, so here's just a couple of examples of acids on the pH scale. All right. So a strong acid has a pH between 1 through 3. 1 to 3. That's a strong acid. All right. They produce lots of hydrogen ions. Now, bases, remember, they're between 7 and 14. So if you're between 11 and 14, that means you are a strong base. All right, a strong base, meaning you're producing a lot of hydroxide ions and a lot less hydrogen ions. Okay. All right, now we're going to talk about buffers. All right, buffers are used when you have either a strong acid or a strong base, because when you get a strong acid or a strong base, that can be very harmful. All right. If you've ever been in a pool before, and it could be the same pool, maybe you went swimming, 2 weeks ago, and you could swim, open your eyes, and everything will be fine in the pool. No burning or nothing. You could swim for 5 hours straight, open your eyes the whole time up under the pool, and nothing's wrong. But then you could go back to that same pool maybe 2 weeks later, and you open your eyes for 1 second, and the chlorine is so strong in the pool, and it's burning your eyes, or you swim for an hour, and you get out and your eyes are all red. That's because there's a pH imbalance. That means it's too acidic in there, or it's too basic in there. So if it's a lot of chlorine, then it's probably too basic, which means they need to put some buffers in. A lot of times you see them like, I forget what it's called. Some people call it pool salt, or it's just like pool cleaner or pool neutralizer. It's actually a pH neutralizer. Pretty much what they're doing is putting in buffers. And what a buffer does is a buffer is a weak acid or a base that reacts with strong acids or strong bases to prevent sharp, sudden changes in pH. All right, so basically it neutralizes it, meaning on that scale, it brings it closer to neutral. Okay, so if I go back like this to this scale, remember 7 down there where pure water is, that's neutral. So if the chlorine is burning your eyes and it's up at 11, you would put a buffer in to bring it closer back down to 7. Okay? That's called neutralization, when you take a strong acid or a base and bring it closer to neutral. All right, so there goes your examples. You have a weak acid, like vinegar, and a weak base, like Dawn dishwashing liquid. Those are both weak acids and bases, and those can be used as buffers. Buffers are also produced by our body, all right, in a natural way in order to help maintain homeostasis.